We're continuing here with Faraday's law. This is chapter 29. And here we are taking on an understanding of, or addressing an understanding of, the fourth of Maxwell's equations. We've done 29.1 where we've looked at Faraday's law. In 29.2 we now look at Lenz's law and the motion of a conductor in a magnetic field. Well, Lenz's law states that if we have an induced EMF, or electromagnetic field, it will create a magnetic flux that opposes the change in the magnetic flux. This is kind of like a Murphy's law. In other words, whenever you induce a change, it will make a change reversibly that tries to make that magnetic field smaller. So if I try to increase the magnetic field through a loop, then that will create a current that goes around that loop, and that current will create a magnetic field that opposes that change, whether that change is positive or whether that change is negative. And that's the reason for the minus sign that occurs in Faraday's law. Now, an application that I would like to show you that kind of exemplifies his law is a very interesting one. I want to take a conductor of a certain length, and I want to put this in a crossed magnetic field. So there's a magnetic field everywhere here. Here's our magnetic field, B. And this is a loop right here of wire, and this is a bar, and I'm going to take this bar and I'm going to slide it this way with a velocity V. Now when I do that, you can see that I change the flux that's contained in this circular area. And you'll recall from Faraday's law that the voltage is going to be equal to, that's between the that's generated around this loop, is going to be equal to the negative of the derivative. Of course, that's just from Lenz's law, so we forget that for now, equal to d by dt of the integral of b dot d sigma. Well, b is constant throughout this whole region, and sigma is going to be equal to, let's say this thing has a length s, so this distance here is s, and it's going to move with a velocity v, so we can write this as d by dt, a constant magnetic field B times the area that's inside. Well, what is the area inside? It's the height, s, times the length. Well, what is this length here? It is the velocity times the time. Okay, so we have to take that derivative. Well, this is pretty straightforward. This is constant, this is constant, this is constant, and we take d by dt of t, and so we simply get VSV. So the voltage is B times S times the velocity that is generated if I take a conductor of length S, move it with velocity V within a magnetic field B. Well, you can say, I can just actually forget this wire because the voltage is induced by having this conductor cross over the magnetic field. And that's what does it. So I could actually imagine a little guy, got his two hands here, takes a copper rod between the two, and what he does is he's got a magnetic field that's very strong, and he takes the bar and he just picks it up off the ground and it crosses those magnetic field lines. Well, if he moves it fast enough, let's say it has a length, it might have a length of 1 meter and 1 Tesla, and if he does that with 1 meter per second, you can see that he would have 1 Tesla times 1 meter times a velocity of 1 meter per second. If he can bring it all the way up to countertop level in 1 second, he would get 1 volt. Well, that's kind of amazing. Now, what would he need to electrocute himself? Well, it turns out that a Tesla is a very strong magnetic field, and you remember that the Earth's magnetic field is only about 10 to the minus 4th Teslas. So he would have to move it at a speed of 10 to the 4th meters per second to even get his 1 volt. To get 100 volts, which would be enough to really shock him, he would have to do what? In the Earth's magnetic field, he would have to, since the magnetic field B is so small, he'd have to get a voltage that's large. He would say, okay, I'm going to take the Earth's magnetic field, 10 to the minus fourth Teslas, take a 1 meter length, and I've got to move it at a speed of what in order to get over here a voltage of 100, or 10 to the 2. Well, if this is his velocity right here, then you can see that if I divide through by 10 to the minus fourth, that gives 10 to the 6. So the velocity has to be 10 to the 6 meters per second. Well, that's 1 million meters per second. And that is extremely fast, and that's never going to happen. So we don't have to worry about walking around and picking up pieces of metal or pieces of pipe that we're going to electrocute ourselves, because we're never going to be able to pick them up that fast. But if the Earth had an intense magnetic field of something like 100 or 1,000 Teslas, this could be very dangerous. We wouldn't be able to pick up pieces of metal without electrocution. It's just kind of an interesting problem. And of course, this can be given as an equation on a test, and it's appropriate to do that.